Hi everyone, in this video we're going to be starting chapter 7, which is on normal probability distribution. So we're going to begin with properties of the normal distribution. So the first thing is to use uniform probability distribution. So here's an example so we can start to understand this uniform probability distribution. Imagine that a friend of yours is always late. Let the random variable x represent the time from when you are supposed to meet your friend until he shows up. Suppose your friend could be on time, which x would be 0 in that case, or up to 30 minutes late, so x would be 30, with all equal intervals of time between x is 0 and x is 30 being equally likely. So for example, your friend is just as likely to be 3 to 4 minutes late as he is to be 25 to 26 minutes late. Our random variable x can be any value in the interval from 0 to 30. And so we can use our interval notation, x is greater than or equal to 0, less than or equal to 30, because any two intervals of equal length between 0 and 30, to include 0 and 30, that's what inclusive means, are equally likely, the random variable x is said to follow a uniform probability distribution. So a probability density function is an equation used to compute probabilities of continuous random variables, and it must satisfy the following two properties. Number one, the total area under the graph of the equation over all possible values of the random variable must equal 1. So real quick, we've learned about the binomial probability distribution function, this probability density function, because it's an equation, okay? There's graphs associated with equations. So getting into the math part of it. And so if the graph represents the equation, which the equation represents this function, we're told that the area, total area under the graph is must equal 1. So the whole area is 1. That's sort of the same thing as saying, like we've seen in the past, probability can be no greater than 1, and it can be no less than 0. So the height, number 2, of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So we've seen these ideas before with probability. We're just relating it now to equations and graphs. So like I mentioned just a moment ago, probability can be no greater than 1, and it can be no less than 0. And so the height of the graph has to be greater than 0, and then the total area has to be less than, or actually must equal exactly 1. Okay, so let's take a look at this graph. This graph illustrates the properties for the late example, your friend being late. Notice the area under the rectangle, or of the rectangle, is 1. So this whole area, if you computed it, it would be 1. And the graph is greater than or equal to 0 for all x between 0 and 30. And that's this, like, think of it as a vertical value or y value. If this is your y-axis, this is always 0 or more. Okay, it's never less than 0. And so because the area of a rectangle is height times width, and that's from what we know from geometry, and the width of the rectangle is 30 in our example, the height must be 1/30. That's how we got this value here. Okay, and so if you could do a division. So we know the area is 1, we know that the width is 30, so if we just divide the area by the width, we get the height of 1/30. And so this is the density is represented by the height, and then our random variable represents the horizontal axis. In this case, it's time. So the area under the graph of the density function over an interval represents the probability of observing a value of the random variable in that interval. So if we want to know a specific probability, let's say between two values of our random variable, what we actually do is we calculate the area under the graph of that interval. So we're going to figure that out here with this example. So from our same situation with our friend that's late, what is the probability your friend will be between 10 and 20 minutes late? Okay, so we want to actually find the area of this shaded region. So the width of the shaded region is 10, because that's the difference from 10 to 20 minutes. It's just quick subtraction. 20 minus 10 would give us this width of 10 minutes. And then the height goes all the way up to the top of our rectangle, which we already figured out was 1/30. So this area is width times height, so 10 times 1/30th, which is 1/3. And so the probability your friend is between 10 and 20 minutes late is 1/3, or about 33%. Now let's do this one. It's 10 a.m. There's a 20% probability your friend will arrive within the next blank minutes. Okay, so the area of the shaded region in our graph here represents 0.2, which is 20%. Now, the difference in this one from the one we just did is we don't know the minutes that they are late. So notice this is represented with x sub 0 or x naught. It's an unknown variable value of our random variable that we're trying to find. So we need to determine the width of the rectangle so that the area, remember the area represents our probability, so the area is 0.2 or 20%. So we just use our area formula a little backwards, and we know that the area is width times height, and so we just set this unknown width times our known height of 1/30th equal to our area, which is our probability, 20%. And then if you just do quick division, or the other way, you could divide by 1/30th or just times by 30. And then that way you've solved for this unknown width, x naught. And so we get that this time is 6. And so there's a 20% probability your friend will arrive within the next 6 minutes, or by 10:06, since we knew it's 10 a.m. right now. All right, next let's graph a normal curve. So in math, a model is an equation, a table, or a graph, and it's used to describe something in real life. The red curve in the figures below is a model called the normal curve, which is used to describe continuous random variables that are said to be normally distributed. So the blue bars are from our histograms, and then notice the red curve. In each of these examples, the red curve looks remotely or relatively the same. And so that's our normal curve, this red that's kind of in the background here. And so if it follows this type of red curve where it goes up, it symmetrically comes back down, that's considered normally distributed. And so a continuous random variable is normally distributed, or another way to say that, has a normal probability distribution if its relative frequency histogram has a shape of a normal curve. So what we just saw. Okay, so here's another picture for us. The points at x equals mu minus sigma and x equals mu plus sigma are called inflection points on the normal curve, and the points on the curve where the curvature of the graph changes. So let me explain this. This is getting a little mathematical here, but remember real quick, mu represents your mean or average. Sigma represents your standard deviation. So the average or mean is right here in the middle, and then this is one standard deviation to the right, or greater than the mean, and this is one standard deviation to the left, less than the mean. And then these points, if you move over on your horizontal axis, left or right, and then go up to your curve at these points, we call these inflection points because the graph changes what's called concavity. So technically in between here, this is considered concave down. And then right here at this point, notice what's happening to the blue curve. At that moment, it actually starts curving upward. So even though it looks like it's going down to the right, the curve itself is still curving upward. One way to think of it is like a bowl. This one's curved down. It's like a bowl flipped upside down. And then over here, this is like a bowl facing right side up. Same thing on the left. It would be like a bowl facing right side up. So the figure here shows how changes in our mean and our standard deviation actually change the position or shape of a normal curve. So this first one, if we increase the mean, just going from 0 to 3, cause the graph to shift 3 units to the right. It still maintained its shape, but it shifted. So if originally we're saying the mean was 0, and now if we just said the mean is 3, it's the same exact curve, but it's just shifted 3 units to the right on our horizontal axis. And then the next figure, if we increase the standard deviation and we're going to increase it from 1 to 2, it actually caused the graph to become flatter and then more spread out, but it did maintain the center location. So adjusting the mean moved the center of the curve, and adjusting the standard deviation didn't change the center, but it did change the height of the shape. So originally, with a mean of 0 and a standard deviation of 1, we'd have this red curve. And just by increasing the standard deviation, it sort of flattened out the curve. It got pushed like downward, which spread it out more to the left and the right. Next, let's state the properties of the normal curve. So properties of the normal density curve. Number 1, it is symmetric about its mean, mu. So we've seen that in our images. The left and the right side are symmetric. They're like mirror images around the mean. The mean's in the center. Number 2, because the mean equals the median, which equals the mode, if we have a normal density curve, so remember, this is not always true. These three don't always equal. But if it's a normal density curve that is equal, the curve has a single peak, and the highest point occurs at the mean, which is the same as the median, which is the same as the mode in this case. And then number 3, it has inflection points at the mean minus the standard deviation and the mean plus 1 standard deviation. We saw that a little earlier as well. Number 4, the area under the curve is 1. So if you computed all the area under the curves, you would always get 1. Number 5, the area under the curve to the right of the mean equals the area under the curve to the left of the mean, which equals 1/2. So let's make this make sense real quick. Remember, symmetry is happening with your curve. So the right side and the left side are symmetric. They're like a mirror images. If the whole area is 1, if you slice your curve in half at the mean, then the right half is 1/2 area and the left half is 1/2 area. Number 6, as x increases without bound, so it gets really big, it keeps getting larger and larger, the graph approaches but never reaches the horizontal axis. And then as x decreases without bound, gets more and more negative, the graph approaches but never reaches the horizontal axis. That was just our curve looking like it's getting really close to the horizontal axis and just sort of, it never really touches, but it gets super close as we get really large x values and then really small x values. Number 7, remember the empirical rule? We learned about this in the past. So approximately 68% of the area under the normal curve is between 1 standard deviation from the mean and the other standard deviation from the mean. So 68% of the area is the mean minus standard deviation, the mean plus the standard deviation, between those two x values. And then also part of our empirical rule, 95% of the data was between 2 standard deviations from the mean. So to interpret that with area, 95% of the area is between the x values where one of them is the mean minus 2 standard deviations and the other one is the mean plus 2 standard deviations. And then this is a third part to our empirical rule. 99.7% of the area is between 3 standard deviations from the mean. Okay, so here's a picture for what we just talked about. Hopefully, if you're a visual learner, this makes a little bit more sense. So here's the mean right here in the middle. We do have our normal distribution curve. And so what the empirical rule says is if we move 1 standard deviation smaller than the mean and 1 standard deviation greater than the mean, within that region, that's 68% of our area or data from the past. So in this case, it's area. If we move out a little further left and right, 2 standard deviations less than the mean and greater than the mean, and we put that together, if we add the 68 plus this extra 13.5 here, 13.5 here, that's where 95% comes from. 95% of the area of our curve is within this range here. And if we spread out a little bit more, go 3 standard deviations less than the mean, 3 standard deviations greater, then notice your whole curve is almost covered here. We have almost a full curve, and so 99.7% of our area is within 3 standard deviations. And then just a quick note, notice what's happening with the curve. It is getting closer and closer to our horizontal axis if we kept going to the right or if we kept going to the left. So that was something we mentioned for part of what we just went through. Now let's explain the role of area in the normal density function. So example, the relative frequency table, or relative frequency distribution in this table here, represents the heights of a pediatrician's 3-year-old female patients. The raw data indicate that the mean height of the patients, remember mu is mean, is 38.72 inches, and then the standard deviation, sigma, is 3.17 inches. Okay, so notice we have intervals, height between two numbers, 29.0 to 29.9, 30.0 to 30.9, and so on, all the way up to 47.0 to 47.9, and then the relative frequency in each of those intervals. Okay, so we're going to draw a relative frequency histogram of the data and then comment on the shape of the distribution. Okay, so here's our relative frequency histogram, and you can use technology to graph this if you want. Just plug in the values from our raw data table. And so relative frequency is the heights of our rectangles, and then the width is our height in inches from the children. And so if you kind of look at what's happening here, if you were to draw a curve, it is fairly symmetric or bell-shaped. The curve would go up like this and down like this. So it is a nice symmetric or bell-shaped curve. So next, let's actually draw our normal curve with our mean and standard deviation onto the relative frequency histogram. And then once we've done that, we'll compare the area of the rectangle for heights between 40 and 40.9 inches to the area under the curve for those same heights. Okay, so here is our curve put onto our histogram. And so the normal curve describes the data pretty well. Notice that our data fits really well under this curve. And so we can conclude that the heights of 3-year-old females are approximately normal with this mean and standard deviation. And then notice right here is our interval we were told to specifically look at between 40 and 40.9 inches. Okay, so focusing on this specific interval from 40 to 40.9 inches, the curve, the area under the curve, is really close in this region to the area of the green rectangle. So they are approximately the same if we were to compute the area under just the blue curve and not think about the rectangle itself, and then separately think about just the rectangle and not the curve. The areas are very close, and so what we can do is we can use the area under the normal curve to approximate the proportion of 3-year-old females that have this height. Okay, so the equation or model used to determine the probability of a continuous random variable is called a probability density function, or PDF. And then the normal probability density function is this equation here. Okay, so it looks very mathematical. You don't have to compute this by hand very often. You can use technology. But just notice what we have going on here. So we have 1 over the standard deviation, and then we just have some numbers we're going to multiply that by. So in the denominator, times by square root 2 pi, and then multiply that number by the number e, which is about 2.71, raised to this power. And this exponent here, what you have is just plugging in your standard deviation right here. It gets squared in times by 2, and then plug in your mean right here. So x minus the mean, square that number, and then put a minus sign, or just a modified version of it right here. Okay, so don't feel threatened by this equation because we can use technology. We won't use it often or in this class, but instead we're going to use normal distribution in our graphical form by drawing the normal curve. So you can use this equation or you can look at the graphs, and we're going to focus on the graphs. And so the area under a normal curve Suppose that a random variable x is normally distributed. Remember, that means that it has that symmetric bell-shaped curve where the mean is mu, standard deviation is sigma. The area under the normal curve for any interval values of the random variable x represents either the proportion of the population with the characteristic described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. So if we think back to the example we just did with the heights of the children, we can look at a specific interval of heights, so between 40 and 40.9 inches, and see the proportion of that sampled population that had that characteristic or that height. And then the other way this can be interpreted is that it can be the probability that if we randomly select one of those children from the population, it can tell us the probability that they're going to have that height. Okay, so for example, the serum total cholesterol for males 20 to 29 years old is approximately normally distributed, and the mean is 180, and the standard deviation is 36.2. Okay, so first we're going to draw a normal curve with the parameters labeled. Okay, so here's our normal curve, and so what we want to make sure we label is the mean. It's going to be the center of our nice, normal, symmetric curve, and then we want to label one standard deviation to the right and one standard deviation to the left. And so notice how you get these numbers. You take the mean, 180, plus 36.2, which would give us 216.2. And then over here, 180 minus 36.2 is where 143.8 came from. Now, an individual with total cholesterol greater than 200 is considered to have high cholesterol. So we want to shade the region under the normal curve to the right of 200. Okay, so we have 200 right here. We knew that one standard deviation was a little bit further to the right than this, so from the mean. So 200 is about right here, and we're shading the region to the right of that, and that's representing total cholesterol greater than 200 or more. So suppose that the area under the normal curve to the right of 200, suppose that we know that the area is 0.2903. Okay, so we didn't calculate it, we're actually being told what that area is. So suppose we know that area. And so we're going to provide two interpretations for this result. Okay, so our interpretations are, if we know the area of that shaded region, one, the proportion of 20 to 29-year-old males that have high cholesterol is about 0.2903, or 29%. So you could say 29% of males from 20 to 29 years old have high cholesterol. And then the other interpretation is that if we randomly selected a male between 20 and 29 years old, the probability that they'll have high cholesterol is about 29%. Okay, so that's our introduction to our normal curve and normal distribution. That's it for this one.